Okay, thank you. Let's get started. Let me have your attention, please. Let's get started. Welcome to the University of Tennessee Nuclear Engineering Department Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker. But before I do that, I need to make a comment or two. First of all, today's presentation is not directly nuclear related. We try to do that at least once and sometimes 2 or 3 times a semester to be exposed to technology that is outside of the nuclear arena. And today's presentation will be one like that. And then secondly, our speaker, whom I'll introduce shortly, several years ago, he had surgery on his vocal cords. And through a miracle operation, he now has new vocal cords, but his voice is quite soft. And so we did the test. I could hear him from the back of the room when there was nobody here. So it's important that you be really quiet so that you can hear today's speaker, who is Dr. Bob Abernethy. He was the manager of reliability and safety, now retired with Pratt & Whitney Aircraft Corporation. Bob received a BS in mechanical engineering from RPI in 1952. And then he followed that up with an MBA from RPI in 1958. Then he went across the ocean and went to Imperial College at the University of London, where he received an MS in mathematics in 1964, and then a PhD in statistics in 1965. Following his formal education, he joined Pratt & Whitney Aircraft Company. He was with that company for 32 years. He retired in 1987. And since that time, he's had his own quite active consulting firm where he teaches classes on statistics, particularly Weibull distributions around the world. So with that introduction, ladies and gentlemen, please welcome Dr. Bob Abernethy.
Thank you, Professor Dodd. I'm very pleased to be here today. Can you hear me? If you can't, raise your hand. I'll try and speak a little louder. The problem is that this is all the volume I have. So I sound funny. I had a bout with cancer in 1978 and lost my vocal cords. And I had a miracle operation where they made me some new ones out of scar tissue. You can hear me fine. I have to make one comment to Professor Dodd about his judgment. He's invited an Irish storyteller and limited me 1 hour. Actually, I have about 1,000 stories to tell you. So we'll get started. We're going to talk about the golden age of aerospace. But before I get into those stories, I have one story about nuclear physics. 50-some years ago, I was a young engineer at Pratt & Whitney Aircraft in Connecticut, and I needed a set of gas tables for air. So I wanted to go to the library, which was located at United Aircraft Research Laboratories a few miles from Pratt & Whitney. I'd never been there, so I wandered around. I opened the wrong door and walked into this big room. There were black cabinets all over the room, sort of humming. And a guy walked by, and I stopped him, and I said, "What's this?" He said, "This is a computer." I said, "What do you do with a computer?" I'd never seen one, of course. He said, "Oh, we're modeling Pratt & Whitney Aircraft's nuclear aircraft engine." This was a serious security violation, which went on his record. And, of course, I got to meet the security people. And we had a little conversation that went like, if you talk to anybody, you die. But what a glorious concept. A nuclear aircraft engine. Airplane could fly forever, no fuel. So I was really upset, depressed, because I was working on air-breathing engines. I figured in a year or two, I'd be out of work. So I went to the Hartford Graduate Center, which is an extension of Rensselaer Polytechnic, and I took a year's course in nuclear physics. so that I could switch over when the air-breathing engines were obsolete. And of course, the nuclear engine didn't exactly work out too well, as you probably know. Pratt & Whitney spent 10 years on it and several $billion. One of the problems was that the crew could only last a little longer than one flight. So having found that out, they decided to move the cockpit forward, and then they could last maybe 3 flights. So that wasn't good enough, so they added lead plates. Now, in airplanes, lead plates, not a good idea. So they went from 2 engines to 4 engines to finally 6 engines. And they still didn't have enough power. This thing was now the size of a football field. So they decided to get a more energetic fluid. They were using heavy water. They went to liquid sodium. Can you imagine if that thing had crashed? So finally the Air Force said, maybe that's not a good idea. But anyway, actually, I'm here to talk about the golden age of aerospace, the 50s and the 60s. Some of the stories I'm going to tell you are actually true. It was the very best of times. It was very, very exciting. And in contrast to today, we worked in very, very small groups. We had immediate access to the top people. And, you know, for me as a young engineer, I worked with Charlie Lindbergh, for example. I was like this. You know, I worked with Jimmy Doolittle, Juan Trippe as a young engineer. Never happened today. Of course, the best part of it was not only the people we met, but the engineers and the engineering aides and the technicians and the pilots, most of all. But with regard to the pilots, when we got into the Blackbird, there was a secret organization known as the Roadrunners. And I'd heard about it, but we were never allowed to communicate with a Roadrunner. A Roadrunner was a CIA pilot of either the U2 or the A-12 Blackbird. You had to be a CIA pilot in order to be a member. And so they were prevented, for security reasons, from talking to Pratt & Whitney engineers and vice versa. Well, in March 2004, the U.S. government declassified the Roadrunners, those of them that are still left. I got a call that the Roadrunners wanted to have a reunion with the Pratt & Whitney engineers that worked on the Blackbird. And of course, I was very excited about this, and they asked me to be the keynote speaker. And I had to say no, because I was already committed to be co-chairman of a conference in Houston, Texas, the same day, March 2004. So I had to refuse. Well, the CIA, the Roadrunners, refused my refusal. They said, you've got to come. They said, can you get your co-chairman to take over by 1 o'clock in Houston, Texas? I said, I think I can do that. They said, well, we'll get you to Burbank, California in time for cocktails. I said, I don't think so. How are you going to do that? They said, don't ask. But they did. And that was the first time that I told some of these stories. And by the way, Pratt & Whitney was rather nervous about this because of the title, you know, Never Told Tales. We're going to talk about top secret black projects in here, Never Told Tales. But anyway, it was a lot of fun. One of the 2 project engineers, program managers you'd call them today, in Florida, I should explain the organization, Pratt & Whitney Commercial Division and Manufacturing is in Connecticut. Pratt & Whitney, Florida was military engines, and specifically classified military engines. At Pratt & Whitney, Florida, there were 2 project engineers, Bill Brown and Dick Mulready. And Dick Mulready wrote a book about this called Advanced Engine Development at Pratt & Whitney, a wonderful little book. Very easy to read if you ever want to get a copy from SAE. But the preface to the book says, this book celebrates the wonderful projects on which we worked at Pratt & Whitney during that almost magical quarter of a century after World War II. It was a time when going to work was fun, with a new challenge almost every day. The feeling of loyalty, both upward and downward within the company, was palatable. The work was pioneering, never having been done before, and it was very exciting, unquote. The man in the middle is Dick Core. This picture was taken just a few years ago. He was the chief engineer for both Pratt & Whitney, Florida and Connecticut. Flew back and forth every week. And in Florida, this is one of his two project engineers, Dick Mulready, who did all the work on liquid hydrogen rockets and jet engines, and we'll talk more about that later. In 1955, I was discharged from the U.S. Navy. I'd been on destroyers during the Korean War, and I joined Pratt & Whitney in the J-75 Engine Development Performance Group. The J-75 was the most advanced engine in the world, and also the most powerful. It powered the F-105 Thunder Chief, the 106 Delta Dart, the North American F-107, the Boeing 707, the Douglas DC-8, just about everything, and the U2. This is a picture of the engine and the U2. For performance analysis, we had no computers. We had no calculators. So every engineer had a 6-inch slide rule in his pocket right here. And on our belt, we wore a holster with a 10-inch K&E log duplex slide rule. Everything was done with slide rules. If you went to an engineering meeting, the first thing you did was take your slide rule out. Because no computers, no calculators. On a good day at Pratt & Whitney, after I learned how, with a good engineering aid, if I worked all day with an hour's overtime, I could calculate 1 point of performance for the J-75 engine. Just stop and think about that. Today, you know, it'd be click, click, and that's it. But it was a different ball game in those days. One morning, Wright Parkins, the president of Pratt & Whitney, had 3 admirals in his office to witness the first test of a new design of the J-75 engine. And I was assigned to that new design. The admirals asked for a plot of fuel consumption against thrust, and they sent a senior project engineer down to my boss, Norm Cotter, to get this plot. So Norm called me over and said, give me a plot of fuel consumption against thrust. I said, Norm, the engine hasn't run yet. We don't have any data. There is no plot. Norm told the senior project engineer, and he said, you've got to have a plot. The admirals want a plot, you've got to have a plot. So Norm looked at me and he said, well, go fudge a plot. Well, in those days, we did everything by hand. So I took out my triangle and my French curve and a pencil and did all the labeling and all this. Probably took, 15, 20 minutes. And I put in a curve. Thrust-specific fuel consumption against thrust. And we took it to Norm. The senior project engineer is standing there breathing hard. He wants this as soon as possible. Norm looked at it and he said, no, Bob, it's too high. Not good enough. The new engine will probably be better than that. I said, Norm, how much better will it be? He said, about that much. Go do it again. So I went and did it again. And I brought it back to him and handed it to him. He said, yeah, that looks about right. And he hands it to the senior project engineer. He says, now you got to get us a copy of this. Whatever you do, you're going to go right by the Oslin machines. That's what we call Xerox machines in those days. Copy machines. You got to get us a copy. Senior project engineer looked at it and he said, no, this is no good. This is just a curve. We need data points. Cotter looked at it and said, we don't have any data. He said, put data points on it. So Cotter pulled out a symbol maker and handed it to me. He said, put some data points on that plot. He handed it to the senior project engineer, and he ran off with a plot. And I went back to my desk, and a few minutes later, I got a call from Mo Kuchera, my good buddy. He was the senior test engineer on this new engine. And he was in the test cell. And he said, come on down, I've got the engine at idle. So I went down to the test cell. The test cells in Pratt & Whitney they're concrete, and they're about 60 feet high, U-shaped. Air comes down one side, the engine's on the bottom, and the exhaust goes up the other side. The test cell is just above the engines to one side, and there's two little windows about that size that you can look at the engine while it's running. Well, I got down there and went over to Mo, who was looking through the window at the engine at idle. The test foreman was over here standing by the throttle, and Mo said to me, the design department says we've got a little problem, high cycle fatigue around 7,000 RPM, so I'm not supposed to linger there. I've got to go right through 7,000 RPM. Well, just then Parkins and the admirals arrived, and they crowded on the other window, and Mo tells the test conductor, go ahead and accelerate to 9,000 RPM quickly. Well, the engine blew up. Fire all through the nacelle, turbine just spinning around. Parkins and the admirals left. The next morning, Parkins, the president of Pratt & Whitney, got a phone call from the Navy. They really liked the new fuel consumption. Much better than that old engine. Send us 6 more copies of the plot. Well, guess what? The senior project engineer never made a copy. So Norm Cotter calls me over and said, how did you fudge that plot? We had lots of fun. We fudged another plot and made 6 copies. In late 1957, Pratt & Whitney had 2 secret, actually top secret, black projects, both of which were going to use dangerous fuel. One was going to use a poison fuel. That is where not only was the fuel poison, but the exhausts were poison. Can we test these in the middle of Connecticut? Where should we go to test them? Well, it turned out that personnel said we could hire more engineers in Florida than any other place. So how about the middle of the Everglades? So that's how I got to Florida, and been there ever since, at least in the summers. But anyway, this was our Research and Development Center, as it was called. I was assigned to the J-58. Now, the J-58 originally was a Navy engine, and the mission was a Mach 3 interceptor. But it was only to go to Mach 3 for 15 minutes or less. And it was going to use this poison fuel. So problem number 1 was, what do we do with poison fuel? So we built this huge swimming pool out there in the Everglades. We're about 22 miles west, out in the middle of the Everglades. Built this huge swimming pool in a big tower, 100 feet high. And the idea was we would exhaust into the bottom of the swimming pool and centrifuge the poison out of the exhaust. But of course, we didn't have any great confidence that it would work. And we're a little nervous because if it didn't work, we just wipe out the Palm Beaches. At the very last moment, the Navy canceled the poison fuel and canceled the engine. So for some period of time, the engine had no home, but we figured someplace we would find a home for this engine. Meanwhile, the other project was in a different part of the Everglades nearby, and I could hear them testing, and it was the weirdest sound. It sounded like someone was torturing a cat. I couldn't understand what it was. And the actual code name, which was secret in those days, was the Sundan Project. and their engine number was 304. And what it was a liquid hydrogen turbojet engine. The security was so tight that we were not allowed to socialize with the engineers in the other project, even though some of them were our good friends. We're not even allowed to talk to them. In the cafeteria, we had to eat in divided partitions so that we wouldn't communicate with each other. My first job on the J-58 was to create a computer program. And this was the very, very first one ever successfully created at Pratt & Whitney. That is, we wanted to be able to use a computer to calculate the thermodynamic and aerodynamic performance of the engine at different flight conditions, at different throttle positions, and so on. So I was ordered to create this, and I was assigned a computing analyst, and we spent the winter of 57, 58 traveling back and forth from Florida to Connecticut. The computer was in Connecticut, building this computer program. And I learned a lot from formulating the model. It made me examine each one of the components, the compressor, the burners, the diffuser, turbines, and so on. I quickly understood that the J-58 engine, as designed, would never get to Mach 3. There were insurmountable problems. For example, at Mach 2.5, the inlet pressure equaled the exhaust pressure. Does that sound like a lot of thrust? And above that, the exhaust pressure fell off. The compressor was deep in surge, 30% negative surge margin. That is, it would be surging if you ever got to that Mach 3. The front stages were stalled. Essentially, the angle of attack was too small on the blades, so they would go into flutter and probably break off. The rear stages of the compressor were choked. That is, you could pass no more airflow through the rear stages. Airflow at high Mach number is thrust, almost exactly. Actually, it's a little more than an even ratio. 1% of thrust is more like 2%. 1% in airflow is like 2% in thrust. So, big problems. One more problem. The afterburner would be at maximum temperature and no cooling air. The inlet air temperatures are like 800 degrees at Mach 3. And by the time it goes through the compressor and into the burners, how are you going to cool the afterburner? The afterburner was made of nickel steel. Melting point of nickel steel is about 2,000 degrees Fahrenheit. The afterburner had to run at 3,200 degrees Fahrenheit, so the afterburner would just plain melt under these conditions. Big problems. So my solution to all of these came to me in October 1958 was to open the bleeds. Now, when we start a jet engine, at least at Pratt & Whitney, the compressor would normally be in surge at starting conditions at sea level. And what we would do is open the bleeds to increase the airflow, take the front stages out of stall. And that works very well. However, you couldn't do this in flight because you'd lose a ton of performance. But my thought here was, if I put ducts on the engine, I could duct that cool, relatively cool air back to the afterburner, bypassing the choke stages and cool the afterburner. So this is actually the drawing in my patent disclosure. I call this engine the recover bleed air engine on the patent. And I went to my boss with this great idea, all excited, of course. I had evaluated it on a very primitive little computer. I had to do all this on my own time, Saturdays and Sundays and at night. It was called an IBM 710, I think. And believe it or not, to program it, Each program statement was a wire. We had these little boards about this size, and you put the wires in for each program statement. I think I had 9 boards to begin with. To get through one point, I'd have to take a board out and put a board in, take a board out and put a board in. Anyway, with this thing, I was able to calculate the performance, and my initial calculation showed big performance improvement. Further, not only could we get to Mach 3, but we could get above Mach 3. But my boss, Norm Cotter, didn't exactly jump at my solution. Actually, it took me 7 months to convince Cotter that the idea would work. One of the problems that he was very much concerned with was that when we opened the bleeds, there would be a sudden increase in airflow, a hiccup, if you will, in airflow. With a supersonic inlet, you can't stand that. You'll pop the shock. Let me explain that to you. The purpose of a supersonic inlet in front of a jet engine is to create a normal shock wave right in front of the engine. The engine cannot eat supersonic air. A jet engine needs subsonic air. So if you create a normal shock wave right in front of the engine, it'll shock from supersonic to subsonic, and then the engine can eat the air. So all supersonic inlets try and create this normal shock wave, which is very tricky. Takes a big plug and a computer program and all that to keep that shock in there. Well, any little hiccup in airflow would pop the shock, and my calculations indicated that that would blow out the engine, and you'd have asymmetrical thrust, only one engine running, and the aircraft would go into a cartwheel and destroy. So Norm was quite concerned about this, and my solution was to go down in Mach number. I showed him that around Mach 2 to Mach 2.2, there would be no bleed flow. If you open the bleed valves, there's no delta P. So we could open the bleed valves at Mach 2 or 2.2 and then accelerate, and then the air would start going through the ducts smoothly. Well, finally, I convinced Cotter in April 1959, and on a Monday morning, Norm immediately went to Bill Brown, the other senior project engineer in Florida. He was our program manager. Bill Brown, quite a character, was Kelly Johnson's big buddy. They had built the U2 together. For those of you that don't know who Kelly Johnson was, he was the genius at the Lockheed Skunk Works, the secret Lockheed development. Probably the foremost genius in aerodynamics in our time. For example, he designed the P-38 fighter for World War II, the Lockheed Constellation, the F-104, the P-80 jet, and of course the U2. Well, Brown and Kelly had set up this management system, a very sophisticated management system. He had a cryptographic phone on his desk, Brown and Kelly. The only ones allowed to touch it were Brown and Kelly. So they had complete control over everything that went on, both with the aircraft and with the engine. It was a man-on-man. No other communications were allowed. Everything went from Brown to Kelly and Kelly to Brown. So anyway, Brown picked up the phone. This is Monday morning, April 1959, and called Kelly. Well, Kelly wanted a Mach 3 plus engine in the worst way. So Brown says, we can build you a Mach 3 plus engine. And Kelly was so excited, he got in his Sabre jet that afternoon and flew to the Pentagon in Washington. And by Friday afternoon, he had the money, believe it or not. And this is the most incredible part of this story. 3 years later, almost to the same day, the airplane flew. He went from clean sheet design to first flight in 3 years. The engine flew with J-75 engines in 3 years. A year later, it flew with the J-58. You could not do that today. Impossible today. You could do that in the golden age of aerospace because we had little tiny groups and no oversight committees or any of that stuff. And I'll give you one quantitative reference for that. Our latest and newest fighter is the F-22, as probably many of you know. Has 2 engines, Pratt & Whitney engines, and the nozzles go this way, movable nozzles. Most advanced fighter aircraft in the world, and it's in operation. It flew for the first time in 1998, very first flight test. I started work on the engines in 1978. So 20 years to build that airplane compared to 3 for Kelly. So it was a very exciting time. A few months later, Brown came screaming out of his office. Abernethy, Abernethy, I figured it out. Recover bleed air. Those are your initials. We're not going to call all of that anymore. And they never did. They never called it that anymore. And one of the strangest things happened. I was transferred to the other project. And to this day, I don't know exactly why. And I've never been able to find out from any of my superiors. They won't talk about it. But I think it was because I knew too much. And Kelly Johnson didn't want any of the engine guys to know too much. By coincidence, my optimization for the engine showed it could fly at Mach 3.2 at 90,000 feet. And that's exactly where the Blackbird flies. So, I was dead on, and then maybe that was the scary part for Kelly. I think it was Kelly, but I don't know. In any event, I got transferred to the RL-10, the liquid hydrogen rocket program. My other recommendation was to use a variable inlet guide vane on the J58 engine. Again, to keep the front stages out of stall. And Bill Brown said, no. That's what General Electric does. General Electric uses variable stators. General Electric does it, Pratt & Whitney doesn't do it. A year later, he put the variable inlet guide vane in, so that was our other contribution. This is the memo I wrote in April 1959. I have a copy in there quoting all the performance. And this is the engine. It wound up with 6 ducts. You can see 3 of them here. The ducts were about that big around, leading from the 4th stage of the compressor back into the afterburner. The rear third or more of the engine, as you see it here, is the afterburner. This was the first engine ever designed to run continuously at afterburner. The Blackbird flies with the afterburner lit all the time, except when it descends to refuel. These were our performance improvements. There's the inlet guide vane. We had an airflow increase of 22%. With my crude little computer, I predicted a net thrust increase of 19%. Actually, I was way off. What I didn't know was that the supersonic inlet was starved for airflow. The airflow schedule for the inlet was much greater than the airflow schedule for the engine. Now, when you have too much airflow coming into the inlet and the engine can't consume it, you have to spill that airflow out, which introduces spill drag. It reduces the thrust of the engine, if you will. So by gobbling up 22% more airflow, I significantly improved the thrust, the installed thrust of the engine. At Mach 3 and above, most of the thrust comes from the inlet, not the engine. The aircraft people used to tease us about that. Of course, you need the engine to suck the inlet down, but the actual delta P thrust forces are mostly on the inlet. And this was the biggie. We improved fuel consumption by 20%. Today, a performance analyst at Pratt & Whitney would give his right arm for 0.5%, let alone 20%. So these were big numbers. We increased the afterburner temperature. We reduced the blade flutter. And this is Bill Brown, the senior project engineer for the J58. He's the guy that built the U2 with Kelly and the Blackbirds. absolutely great engineer from Alabama, of all places. I could tell you a lot of stories about him, but I'll just tell you one. Back in those days, if you had to make a secret presentation, that is, use secret charts, say to go for the Pentagon in Washington, you'd have to roll the charts up. We didn't have any of this. The charts were about this size, paper. You'd roll them up, and you'd put them in this tube about this long. And then they would handcuff you to the tube. And of course, this was embarrassing to travel around in public with the handcuffs on. So you try and hide the handcuffs up your suit coat. Well, anyway, Bill, Brown, and Cotter had to make a secret presentation in Washington. And when they got on the National Airlines first class seats, of course, the stewardess ran right over and said, "Mr. Brown, I'm sorry, but you can't take that in here. We have to put that in the luggage." They always said this to us. And, of course, you couldn't do that. I mean, you're handcuffed to the thing. They put that in luggage, you go in luggage. So Brown said, "I'm sorry, miss, but that's impossible. I can't do that." She said, "Why not? Why can't you do that?" He said, "It's my father's ashes." Well, the stewardess was a little shocked. She went away, and then she came back. She said, "Excuse me, Mr. Brown, but that's your father's ashes. Why is it so big?" Brown said, "He didn't all burn." Norm Cotter said he was keeping from laughing so hard he thought it was an accident. Well, there were many, many problems developing this engine. And, of course, heat was the number one problem. For starters, inlet temperature of 800 degrees. We needed a turbine temperature 400 degrees hotter than anything that had ever been run. And let me tell you, the number one problem, the number one criteria for thrust out of a jet engine is turbine temperature. You go up 10 degrees in turbine temperature, Fahrenheit, you get 1% thrust. That's true today as it was then. So always try and go as hot as you can. We had no idea how to make turbine blades run at these temperatures. The turbine blades would have to run slightly greater temperatures than the melting point of the best nickel alloys we had. So, other problems, the fuel. We had never run fuel over 200 degrees. The fuel here got to 400 or 500 degrees. The oil temperatures were like 400 degrees. You know, we were way beyond anything that had ever been done. And here are some of the temperatures you see for the engine. Really a big problem. The whole airplane had this heating problem, as you probably know, or can guess, and therefore they had to use the fuel to cool the airplane. We also had to use the fuel as the hydraulic fluid for both the airplane and the engine, which heated it up. So, you know, no end of problems here. One of the problems was that we couldn't seal the tanks in the airplane. The airplane grows 7¼ inches in thermally from going from sea level static to cruise altitude. At sea level static, that means the tanks are going to leak like a sieve. Actually, I've heard reports that screaming down the runway, there's streams of fuel a foot high coming out of the wings. The runway is soaked with fuel. Would the afterburners lit? Not a good idea. That's called how to burn up an airport. So they had to find a fuel impossible to ignite, or almost impossible. And the fuel is called JP7. And of course that gave us a little problem. What was our problem? How do you start the engine? You can't ignite the fuel. How do you start the engine? The solution turned out to be a hypergolic fluid called TEB. We put a jigger of this in the main burner. Hypergolic means it explodes on contact with the air. And to light the afterburner, we put in 3 jiggers in the main burner, and the flames would go right through and light the afterburner. So all kinds of problems, as you can see here. There were many control innovations. One of the problems was that if you trim the fuel control, analog fuel control, we didn't have digital controls, trim it at sea level and take off and fly to Mach 3, the pilot had to continuously adjust the throttle to maintain turbine temperature. He couldn't do anything else. So we developed a digital turbine temperature control, which was the very first electronic fuel control ever made. All in all, there were many innovations that today are standard. Today, all jet engines have digital fuel controls. We no longer use analog controls. It was 20 years later, 1980, before I found out what the other project was all about. None of us knew this, but the two projects were competing. Both projects were to go into a high Mach number reconnaissance plane at the Skunk Works. The only one I know that knew this was Dick Core, the boss of the two project engineers, but neither one of them knew it. Kind of a weird situation. The other engine, the 304 Sundan engine, used cryogenic liquid hydrogen, which, by the way, is the perfect fuel. I mean, it has a huge heating value, almost double the heating value of any other fuel. And, of course, the products of combustion are water. Marvelous, marvelous. So the idea was to boil this liquid cryogenic hydrogen behind the burners in this engine and boil it and then expand it through a 16-stage turbine to drive the compressor and then run the hydrogen into the afterburner, and all of this would make great thrust. One more picture of the J-58. I said the afterburner temperature was 3,200 degrees. It makes the nickel alloy afterburner almost translucent, as you can see here. Kind of weird. This is on a test stand in Florida. Oh, and here's a picture of the Blackbird. Before I started, I showed some pictures of the Blackbird. If any of you ever want any of those pictures, they're all on my website, and you can download them. But I think I have 80 or 90 pictures of the Blackbird. Habu was the name the pilots gave to it at Kadena, Okinawa. The Blackbird flew out of Kadena, Okinawa, and Beale Air Force Base, and later from England as well. But initially, Kadena was the operating base. Habu means snake in one of the Arab dialects. And they think this thing maybe looked like a cobra coming at you, which is why they called it the Habu. And there it is, taking off, afterburners lit. It always took off almost empty, so the takeoffs were pretty exciting. And as you can see, afterburners push flame out 40 or 50 feet behind the airplane. They would immediately climb to 35,000 feet and refuel after takeoff. And then, of course, they would accelerate supersonically up to cruise altitude. This is the Sundan engine, and as I mentioned before, it used liquid hydrogen. The flame speed of liquid hydrogen is so fast that the afterburner here is only a foot long, where the afterburner on the J-58, as you could see, was about 7 feet long because of the difference in flame speed. And this was the airplane that Kelly Johnson designed for the 304 engine. It was called the CL-400, and it had the engines way out on the ends of the wings. I've never figured out why. I mean, if you lost an engine, there's no way you could control this airplane, but that's how they designed it. It was designed for Mach 2.5, I think at 100,000 feet. And that's what it was looking like. The engine actually worked pretty well, but the fuel consumption was a little high. And the problem with hydrogen is that it has a very, very low density. That's why if you look at the shuttle, that huge thing in the middle, that huge tank, that's the hydrogen tank. Kelly figured that in order to make this aircraft operational, he'd have to have hydrogen storage tanks around the world, and he canceled the project because of that. So this was competing with the J-58 and the Blackbird won. The interesting part of the story is that after they canceled the 304 project, some genius thought that maybe we could make a rocket engine out of the same cycle, thermodynamic cycle, which we did, the RL-10. And I worked on this for quite a number of years. This was the world's very first liquid hydrogen rocket engine. And hydrogen as a fuel is so good, it gives you a specific impulse, which is like miles per gallon, about 30% higher than any other engine in the world. But in addition to that, this cycle has a unique feature. There's no gas generator. All liquid rocket engines have to have turbopumps, one for the oxidizer and one for the fuel, and they have to be driven by a turbine, and the turbine needs a burner. So all liquid rocket engines have burners, except for this one. This one, we expand the hydrogen, boil it, let it expand through a turbine, and it drives both turbopumps. Now, to boil hydrogen, of course, you need heat in the nozzle, or at least I thought so. The nozzle temperature here would be 4,000 degrees. 4,000 degrees with hydrogen. So no problem boiling the cryogenic hydrogen. But my question is, this is an upper stage engine. It's supposed to be able to go out into space and cruise for weeks or months and relight. In outer space, where's the heat? So my fear was we couldn't start it. And what about it at sea level? No fire in the rocket nozzle. How are you going to start it? Well, this genius said not to worry. It'll start great. Well, I was very much worried. Well, when we turned this thing on, it turned out not only was he right, we didn't know how to control it. This baby goes from 0 to full power in a quarter of a second. The turbopumps go from 0 to 240,000 RPM in a quarter of a second. Of course, we blew up engine after engine. We couldn't stop it, and no way to stop it. So it took us quite a while to figure out how to make it. Well, once we did that, of course, it then had, because of these two features, hydrogen fuel and no gas generator, highest specific impulse in the world. For all liquid rocket engines, this is the winner by far. Nothing else comes close, even today. This is the only engine with this cycle. The French tried to copy it for the Ariane rocket, and they couldn't make it work. So today, practically everything that's gone out to the planets, out into outer space, that hasn't gone on the shuttle or the Ariane rocket has gone up with RL-10s. It's our #1 upper stage engine. Powers the Centaur vehicle and many others, as you can see here. So from the failure of the Suntan engine, we got a pretty good product, the RL-10. They're still in production today. I'm getting down to the point where Professor Dobbs is going to throw me out. Are there any questions? Any questions? I love questions. Yes, sir.
Tell me about the airspeed record.
The airspeed record was...
Let him repeat the question with the microphone.
Could you tell us about the
airspeed
record?
It's not a PA mic.
Oh. His question is, what about the airspeed records? The Blackbirds hold all 17 world speed records and altitude records. And the amusing thing was that when we'd send the Blackbird up and break all the records, which we did a number of times, 2 or 3 months later, the Russians would send up a MiG-25 and break our record. And the next day or the 2 or 3 days after that, they'd send the Blackbird up and break the MiG-25 record. This went on for quite a while. Finally, the Russians gave up. But the truth is, even today, the top speed of the Blackbird is secret. and it's never been allowed to be published. Of course, there are many good guesses. The current world speed record set by the Blackbird was 2,391 miles per hour, which is Mach 3.31, a little bit above my design point 50 years ago. But even that isn't the max speed. The last flight of the Blackbird was from Los Angeles LAX airport to Dulles in Washington, and it was done in 55 minutes, crossing the United States. But what the public doesn't know is that that was done at part power, because the Air Force, even though that was the last flight, it still doesn't want to publish the top speed of the Blackbird, so they did it at part power.
Okay, as many of you know, we do get questions occasionally from cyberspace, from people that are viewing the live webcast. And we got one right before he began his presentation, and let me read it. It comes from Claudia Gibson, who is with the Lilly Aviation Club, and she says, the Blackbird still holds 17 speed and altitude records, even though it is 40 years old. Technology and developmental science being what they are, do you foresee newer versions of the SR-71 Blackbird coming along to take its place? Why or why not?
I guess the answer is yes and no. Initially, the reasons they gave for terminating the Blackbird operationally was that the satellites could do the job. But actually, the satellites can't do the job, because with satellites, you know exactly when they're coming over. And our enemies abroad hide things when the satellite's coming over. So that's a deficiency. The other thing is the satellite is much higher. So the reconnaissance capability of the satellite is not nearly as good as an aircraft. And of course, the U2s are still flying for that very same reason. You can put a U2 up at any time, and the enemy doesn't know when it's coming. The reconnaissance capabilities of the Blackbird are legendary. I've had it on, this is hard even for me to believe, but on good authority, I can tell you that at 60-mile side range, the Blackbirds flew the perimeters of the USSR during the Cold War. Not over the USSR, but the perimeters. 60 miles out, they could identify people on the docks. They could read license plates. I find that very hard to believe, but on good authority, I believe that's true. Something called sideband radars. Somehow they get pictures from those. Any other questions?
Yeah.
I love questions. Yes.
Do we have any questions?
Yes.
If you would, raise your hand, and then so we can get the microphone to you. Dr. Janapal.
A couple of questions. First of all, did you know Bill Sears?
I know the name, yes.
Okay, because he was like the flying wing fellow, and he actually spent some time at University of Arizona, and that's how I got to know him somewhat.
Yes.
And, he passed away recently, unfortunately. And the other question I have is first of all, I enjoyed your presentation very much, but I have a question on the Weeball distribution. Can you give us a little bit of
I'd love to.
Of why that becomes so important?
Oh, God, I'd like to spend a couple of days on that subject. The Weibel distribution is the world's most popular distribution for analyzing failures and characterizing material properties. And it has several unique features, but the number one and most important is very small samples. With the Weibel distribution and no other distribution, we can predict how many outages electric utility will have, or how many accidents an automobile will have, rather accurately with 2 or 3 failures. And we can run laboratory tests with 2 or 3 or 4 failures, where any other approach, you're talking about 30 or 40 tests. So as far as industry is concerned, it's very important to cut costs. As far as aerospace and medicine is concerned, you don't have the luxury there, when you have accidents, of You can't ask them to go crash and burn a few more aircraft. They won't let you do it. And that's the number one benefit of Weibel. And I'd love to come back and talk to you about it. I really would.
Do we have other questions from the local
Another
audience?
one back here. You had a question?
Raise your hand if you have a question. Andrew. If you go.
I was going to ask you about the MiG-25s and the SR-71s. When I was out in Oregon at there's a aircraft museum out there that you're probably familiar with near Portland that has an SR-71 in it. And the guy there told me that he talked to some Blackbird pilots, and I think it was the MiG-20. It was the MiG-25. I believe that the engines were made out of steel because the Russians couldn't afford titanium for it. And so when it went full speed to try to chase the Blackbirds, it would burn out its engines, and they would play with them for a while and accelerate and leave them behind. It was sort of like a one-shot deal. Is that true?
To some extent, that's true.
Okay.
The Russians did use titanium. Actually, the world's largest source of titanium are the Russians. That land mass. But the MiG-25 was never able to catch the Blackbird. At best, it could do Mach 3. When that Russian pilot landed one in Japan, of course, Pratt and Whitney immediately flew a crack team of engineers over there, disassembled the entire engine, and reassembled it, took pictures, ran it on the test stand and all that. And in some areas, they were ahead of us in engine design. Never undersell the Russians. They're very, very smart. I've worked with a lot of them, and I have great respect for the Russians, and in particular in aerospace. They do marvelous things. Our best fighters today and their best fighters are about equal. I forgot about this, but I had some pictures I wanted to give away, and I think you asked the first question, and you asked the second question, and you asked the third question.
All right, do we have any other questions from the local audience? You get a picture if you ask a question.
Again, if you ever want any of these pictures, you can download them on my website.
Okay, we do have a few new faces that we seem to have new people every week that show up. And what the new people probably do not know is that we have a reception downstairs on the second floor, and Dr. Abernethy will be there to join us for the reception, and you can talk one-on-one with him and ask more questions. But before we adjourn to the reception, let's express our appreciation to Dr. Abernethy for his presentation.
Thank you very much. My favorite topic, so thanks for inviting me.
That was great, Bob. Thank you very much.
Thank you.